So what if you could take one really simple, kind of intuitive idea, make hundreds of copies of it, and end up with one of the most powerful predictive models in all of machine learning? Well, that's pretty much the story of the random forest. It's this awesome journey from a single, easy-to-understand tree to a massive, powerful, and incredibly accurate forest.
Okay, let's dive right in. Our story starts with our hero, the single decision tree. And you can really just think of it like a flowchart. It asks a bunch of simple yes or no questions about your data, things like, is this value bigger than 50? Or is the category blue? And it just follows a path down these branches until it lands on a final answer. It's wonderfully simple and super easy to see what it's doing.
But like any hero, this one has an Achilles heel. There's a critical flaw that can make it pretty unreliable, especially when you let it get too complicated. So what is that single biggest weakness? Well, it's a problem we call overfitting. See, a single decision tree, if you let it grow deep enough, can get way too specialized. It starts to basically memorize the training data you show it, learning every single little quirk and all the random noise. But then, when you show it brand new data it's never seen before, it just fails. It can't generalize what it learned, which makes it a really poor predictor out in the real world.
So how do we fix this? How do we get around this fatal flaw? Well, the solution doesn't come from trying to make that one tree smarter. Instead, it comes from a really powerful idea from the real world, the wisdom of crowds. It's this core idea that a whole bunch of diverse opinions is often way better than just a single expert.
In machine learning, we call this ensemble learning. Instead of trying to build one perfect, all-knowing model, we just build a whole lot of them and combine their predictions. By getting a consensus from a ton of different models, we can average out their individual mistakes and get a final result that's way more accurate and way more stable. And this right here gets to the very heart of the random forest. This quote just nails it. The whole point is to average many different deep decision trees. And that averaging process is specifically designed to fight that overfitting problem by reducing the model's variance, which is just its tendency to change wildly depending on the exact training data it sees.
Okay, so we're averaging trees to cut down on variance. Got it. But how does the algorithm actually do this? I mean, how do you stop it from just making hundreds of identical, overfitted trees? Well, the magic is right there in the name. It's all about being random, but in two very specific ways.
So here's the high-level game plan. First, we're going to create a bunch of different random samples of our data. Then, we train a totally separate decision tree on each of those unique samples. But, and this is so important, as each tree is being built, we throw in another layer of randomness by only letting it see a subset of the features at each decision point. And finally, to make a prediction, we just let all the trees vote. The majority wins. Let's break down that first ingredient. It's a technique called bagging, which is short for bootstrap aggregating. The goal here is pretty simple. We just want to make sure that every tree in our forest gets a slightly different look at the data.
Here's how it works. We start with our original data set. Then, to create a training set for tree number 1, we randomly pull data points out, but with a really important twist, we do it with replacement. That just means after we pick a data point, we put it back in the pile so we could totally pick it again. You can see it right here. The first sample has B twice, and C isn't even in there. We do this over and over for every single tree, which guarantees that each one is learning from a slightly different version of the data.
But just giving the trees different data isn't quite enough. See, if there's one really powerful predictive feature in your dataset, most of the trees will probably latch onto that same feature. That would make them all act pretty similar, right? They'd be correlated. So to solve that, we introduce our second secret ingredient, random feature selection. So let's frame it this way. Imagine your data has 100 different features, 100 columns. To force our trees to be diverse and kind of creative, how many of those 100 features should we let any single tree even look at when it's deciding how to make a split?
The solution is just brilliantly simple. We don't let the tree see all 100 features. Instead, at every single decision point, the algorithm only offers the tree a small, random handful, maybe just 10 out of the 100. The tree has to pick the best feature from that small group. This amazing constraint forces each tree to find different ways to make predictions and stops them from all becoming clones of each other. This decorrelation, that's the secret sauce.
So, we've gone through all this effort, right? We're bootstrapping our data, we're randomizing our features, all to build this big, diverse forest. So, what's the payoff? Why is this thing so incredibly popular in machine learning?
Well, there are 3 huge advantages. First, they are just highly accurate.
they often perform incredibly well right out of the box with default settings. Second, because of how they're built, they are naturally resistant to that overfitting problem that just plagues single trees. And third, and this is a really powerful bonus, they can actually tell us which features in our data are the most important for making good predictions.
Now that last point is fascinating, isn't it? How can this big collection of hundreds of random trees tell us which of our data columns are the most predictive? I mean, how does the forest know which features matter most?
The method behind this is as clever as it is powerful. It's called permutation importance. So after the forest is all trained up, we take a single feature, let's say customer age, and we just randomly shuffle its values. We completely scramble the connection between age and the outcome. Then we see how much the model's accuracy drops. If the accuracy totally tanks, well, we know that feature was really important. If the accuracy barely changes, that feature was probably just noise.
Okay, so random forests seem almost perfect. They're accurate, they're robust, they're insightful. But you know, in the real world, every powerful tool has a trade-off. Let's talk about the big one for random forests.
And here it is. While a single decision tree is beautifully simple, you can explain it to anyone, a random forest is not. Following the logic of one tree is easy. Trying to follow the logic of 500 trees all averaged together is pretty much impossible. We trade that simple interpretability for the massive predictive power of the forest, which can often feel like a black box.
Now, even though these models work great on their own, data scientists can squeeze out even more performance by fine-tuning some key parameters. We call them hyperparameters. This means deciding things like exactly how many trees to build, setting a maximum depth for them, and defining how many features each tree gets to see at every split. So, how do they find the best combination of all these settings? Well, they often use tools like something called Grid Search CV, which, as the documentation here says, performs an exhaustive search over all the parameter values you give it. It just systematically builds and tests models over and over again to find the one combination that works best for your specific problem.
And that really brings us to the final crucial question. It's the one every data scientist has to ask themselves, and it's the central dilemma of using a model like a random forest. When is a powerful prediction more valuable than a simple explanation? The answer? Well, that depends entirely on the problem you're trying to solve.